All right, so given something like this, you follow the exact same steps that you did with the last type. Doesn't matter whether the variable or whether the variable's in the fraction or not, or in the denominator of the fraction or not. If you have a fraction, look to get rid of your fraction. And again, you do that by multiplying by the LCD of all the fractions involved. So notice if your denominator does contain some variables, you may have to factor those. So the difference of squares factors into the sum and difference of the terms being squared. And so now it's just a matter of establishing your LCD. You need a factor of x minus 2. You need a factor of x plus 2. And then you need a factor of x plus 2 and x minus 2. You already have both of those. So this is your LCD. You distribute that to each of the terms. And when you do, you're left with, again, it's the same idea. You take the numerator of your fraction times the LCD factor that does not get canceled out. So here the x minus 2's get canceled out. You're left with x plus 2. Take the next fraction's numerator 3 times the LCD factor that's not canceled out, x minus 2. And then minus the last fraction's numerator 6x times the LCD factor that's not canceled out. Well, this one cancels both of them. Okay, so once you do that, it just again becomes a regular solve the equation. And whatever type it happens to be, in this case, it's a linear type. So you're going to isolate your variable and solve. So here, 1 is an identity, so you just have the binomial itself, x plus 2. We distribute the 3. And now we combine all our like terms. So if we add a 6 to both sides, giving us 8 to the left, subtract an x from both sides. Again, that gives us, you can think of it a couple different ways, but it gives us 2x minus 6x leaves us with negative 4x. Divide by negative 4, and you're left with your solution x is equal to negative 2. And now, notice I write this in kind of a different color than I have been. Anytime you have a variable in the denominator, you have a potential for domain restrictions, right? So in this particular case, if you have a denominator that has variables in it, you have to check your solution. This one now isn't just a recommendation, it's a requirement. And because when you test this back in, what do you notice in this expression right here? If we did plug in an x of negative 2, we'd have division by 0, which is undefined. This cannot happen. When you get something like that, it's called an extraneous solution. It's a solution that it worked. You got a solution when you did the algebra of it, but it doesn't fit within the original restrictions on the problem, which in this case was the domain. So in this particular case, your answer would be no solution. Okay? And more specifically, you have an extraneous solution, but it just isn't going to work. Okay, so you do need to check your solutions for all equations with variables in the domain or in the denominator or anything else that would have a potential domain restriction.